All right, let's get rolling. We didn't manage to get other people online, so you're trying to look at the YouTube video. So, as we mentioned in class before, and also in the email, the material for the midterm is Chapter 1 and 2. Chapter 1 and 2. It covers sessions that we've had in class, which are week 1, week 2, week 3, and 4.1. 4.1 was accelerating fluids, both linearly and rotationally. I've also said across the board that the material we'll talk about, well, the exam material, there are 3 questions, each worth 110 points. Full score is 300 out of 330. The materials are pressures, forces on structures. They are manometry and fluid pressures at a point. What's that mean? And material properties. So, viscosity, surface tension, and compressibility. Such things. You can bring a 2-sided piece of paper with you. You can fill it up however you want. You can fill it up with your notes in postage stamp size and bring a magnifying glass, as some people do. You can do whatever you want. So there's no control on that. The exam questions are related to understanding how to kind of put together the problem, and then once I think you understand how to put together the problem, then it all hopefully falls into place. That's my hope anyway. Again, just to repeat, of course, is to bring you up to a standard so you're not a danger to yourselves and other people as you work as engineers and scientists. So that's kind of the desire here. But the scores are curved, only in that we'll take the highest score, which is below 330, and we'll take that score up to 330, and all other scores will follow in going up to that. And so those are kind of the ground rules, I guess, for these tests. They'll follow the tests that we had for the last few years. Maybe there's exams on there since 2009. Some of them are multiple choice. They won't be multiple choice. They'll be written questions. What will happen with the exams is there'll be 3 graders. Each one will take one of the 3 questions, and they'll consistently grade each of the questions themselves, so there is some consistency. Yeah, and that's it. So, yeah, thanks. Yeah, there is, yeah. So, if you get the right answer with working, then I presume the graders will assume that you get full credit. If you don't get the right answer exactly, then I'm sure they will go through there for partial credit. If you get the right answer with no credit, then they'll assume you cheated and they'll probably not be good. So, I mean, that hasn't been an issue in this class. It's a very tiny proportion, 1% or less of the population. But that's it. So, yeah.
About the partial credit, I've noticed in the practice exams or the past exams that a lot of the problems build on each other. So if you screw up the first step, do you get a 0 for everything?
No, you get a 5. Partial credit means you know how to do it. Okay. You might not have used the right numbers. So. Sorry? Same question. Fair enough. Yeah. Yeah, so no. So they are multi-part questions to build, but you're not penalized from the fact that, if you screw up part 1 of part A, then you're completely screwed. You're not. So. Okay. Yes?
Will we get a formula sheet like this, or should we put everything on that?
You need to bring everything yourself. So I don't pretend to know what you need, what you think is kind of common knowledge and not, so you should bring that yourself. So there's nothing up. There are, if you see the other exams, there's a line at the top of them, density of the water, gravitation, acceleration. You know those anyway, right? Some of the things that you might need would be included on the exam. Typically, you've probably seen that if you've looked at those in the past. Anything else? Yep.
Well, we need to know all 3 of these units.
No. SI.
Just SI then?
I don't know anything else in SI. Didn't you notice? And why would anyone need to? That's my other question. But of course, if you work in the oil industry, you certainly do. Okay. Ill-chosen, of course, I would say. Who am I to say something? Ill-chosen that you need to use those units. No, it's a profession. All right. So I'll go through quickly the things that. So I guess the other part of this is that there is no equation that you need that wouldn't be included in the stuff that's in here. I mean, it's not a small set of notes. It's not 120 pages like it would be in real time for what we've gone through in class. It's probably 20. So please cull down a little bit.
Do we need to know what kind of densities should we know, like with regard to fluids?
Water?
Like anything else besides water, or no?
No.
Are there going to be any type of derivations?
No. Except for putting things together, free body diagrams, resulting forces, those kinds of things, but not integrated and differentiated stuff, which I think is what you might. Yeah. Right. So I'll go through this. I'll go through it moderately quickly because we can't expect to go through 3 weeks, three and a bit weeks of work in one evening session. I would look at previous exams. I'd look at the assignments you've done. I'd look at the stuff we've done in class. I won't dwell on this. So we'll go through things at my pace. It'll be moderately quickly. If there are things you want to talk about, then you should stop me. If there are things you want to talk about after we get through to the end, then I'm happy to stop and do some things as well. I'll stay here as long as you need. SI units, I guess, is all we need. Let me grab this chair. So, yes, so what, I don't think you need to know the density of air. Density of water, you know. We've only really talked about these. You don't need to know these because we've only just talked about them in class, maybe. You certainly need to know what a Pascal is, Newton per meter squared. You know what kilograms and newtons are. Possibly need to know that a Newton is a kilogram meter per second squared. I mean, those are standard definitions for you. I won't stay on the equation sheet. This is just summaries. So in terms of material properties, we talked about the ideal gas law. We talked about 2 forms of compressibilities. Yeah, I'm sorry it's not as big as it should be. Ideal gas law. What do you need to know about that? You need to know what you already know. Temperatures are absolute. Pressures are absolute. This is the individual gas constant for a particular gas. And this is density. You know that if we have isothermal compression, then we can just write the ratio of these, and since temperature doesn't change, P over rho is equal to RT. Since temperature and gas constant don't change, then this is the constant, and you can write it between 2 states, one pressure and another pressure if it's a closed volume, and so you can use that. If it's isentropic, then that means that the entropy doesn't change. If you're taking maybe Jeff Brownson's course or Angela's or Lubisha's, whoever's. And isentropic means that there's no entropy change, but it's insulated, and so the temperature can change. And in that case, this is still true, but it's related by an exponent applied to the density, which is the ratio of specific heat to constant pressure and constant volume, which we haven't talked about, which is often around some number, and we haven't really talked in great deal about that. We also defined compressibilities of fluids. Again, just a definition. Bulk density being the change in volume per unit volume as you apply a pressure. Since when you apply a pressure, the volume gets smaller, there's a negative sign. You can also write it in terms of pressures and densities. And we use that in a derivation, which you're not necessarily required to replicate. But one interesting quirk of that, I guess, is that surprisingly, or perhaps interestingly, the bulk modulus of a gas is equal to the pressure. So the bulk modulus of the air in this room is equal to 103 kPa, which is atmospheric pressure. Right? So material properties, ideal gas law, compressibility, two properties. Two other important behaviors or laws, I guess, would be Newton's law of viscosity. And you've certainly done some questions with this in your assignments. The shear stress that you have to apply to a plate is linearly related to the rate of change of velocity in the direction of that shear force with respect to its perpendicular direction, right? So this is, for this particular equation, this is the y direction, this is the v direction, and so really it's the magnitude of this triangle. So if you're going at a very high velocity and it's still a small gap, then this strain rate, it's actually a strain rate, it's a velocity, rate of change of velocity in space. So this is a velocity change in space, has a velocity here, so to get from this velocity to this velocity, if this were it, is a big velocity gradient in space, not in time. And so the larger this is, then the larger the shear stress is that you have to apply to be able to do that. They're linearly related, and the coefficient that just happens to link those is called dynamic permeability, dynamic viscosity. I don't think we've ever used that term because we haven't talked about kinematic viscosity because we haven't needed to yet. And the units of dynamic viscosity are in, you can work it out from stuff we talked about on dimensional, comparing dimensions, or Pascal seconds. And so you've done a couple of examples, I think, in your assignments to look at how to calculate forces on things. And you've seen that in prior tests. And so that's yeah, worth looking at. Okay. So Newton's law of viscosity is one. And the final one in terms of material properties is interfacial tension. And important for lots of reasons, for lots of people who look at fluid flow in porous media, especially with lots of different fluids like gas and oil and water together. It's an important medium where this tube, instead of being a capillary tube, is actually a pore throat, for instance. So kind of a fundamental thing in that regard. And again, a derivation, pretty simple derivation as you recall, basically taking a tube and using a couple of things that we know about this tube. One is that the atmospheric pressure here, because we travel on a straight line and in the same fluid, has to be the same as the atmospheric pressure here. And so we can cut this tube off here, and this should be atmospheric pressure. And if that's the case, then we can just draw a free body diagram which links this to a ring of forces which are planned up here. So I won't rederive that, but no. So in other words, if this is in density, so what is it? So it's 2, he said he won't derive it, but he will. Circumference, interfacial tension, the component of this angle acting vertically upwards relative to theta has to be equal to the weight. And the weight has to be equal to the volume multiplied by density multiplied by gravity. So things that maybe 2 weeks ago were stretching you a little bit, I think probably now you're much more comfortable with those. And so that's the kinds of, so in terms of derivations, you don't have to integrate or differentiate stuff, but you will have to think about free bodies, and because that's kind of the stock and balance of our trade, I think, in some respects, right? And so that's where that expression at the top comes from. I think you already did an example with a bubble inside and outwards in terms of surface tension and how big can a bubble get, etc. So those are the fluid property components. Yes?
In one of the old exams, I think it was the compass one, it was laying on its side.
Mhm.
Is it always going to be 2t is equal to weight on the force diagram?
Wow, you're expecting that I can remember that, and you know, senility sets in a bit early these days, and so I'm not sure I can cast my mind. So this is a needle floating in a piece of cork or something, and then you're talking about a section with two things on it, that a cross section that look like this. Yeah. Well, yeah. I mean, it has to be on both sides, just like in your bubble. If I don't remember this, but in the bubble you had an inside and you had an outside component, right? In that example. So here, yeah. So there's two. If that's what you mean, I think, right? So yeah, you just have to look at where the forces would be. So, okay. All right. So that's fluid properties, I think. And so you should also realize that. Well, you can look at actually what you might do is, I guess it's not up there now. I've taken it down. You could look at last year's video and last year's equation sheet and look at what was on the exam. And so there's no trickery involved here. I'm trying to get you to be able to focus in some way on what you need to know here. So I'm trying to help you at some level. So the equations you see on the previous sheet, I'm not going to go through those. What do we know about fluid pressures at a point? Well, we have a variety of expressions, but this is a pretty fundamental expression for us. It says the pressure as you go up or down changes as a function of the unit weight. The negative sign for us is because we always have the z direction positive upwards. And so depending on where you start with your pressure, then I guess this is negative z, this is positive z. This is always true, of course, and really all it's saying is that if you write this out in this way, you could also write this as this, right? And so this is saying that this is, a change in pressure. This is a change in elevation. So if you think about it, just as similar triangles, pressure and unit weight, this would be unit weight, and this would be 1, just this. So that's an interesting way to be able to think about it. This is always true at a point. It's always been true for us in a liquid because the unit weight doesn't change with pressure very much. And so from that, we can always get a relationship that looks like this. Pressure, so this here would be maybe pressure 1. This would be pressure 2. And this would be H. So you can often use it in this simple form just by being careful about knowing when pressure should increase or decrease relative to the location where you are. And so this is always true for liquids, always true for liquids. I think we did a calculation in class to look at how untrue it was if you went to the bottom of the ocean, and it turned out to be 1 or 2% different from assuming it's incompressible. And so we've done that, so you probably don't need to do that again. So this is always true. This is true only for a liquid, an incompressible liquid, and we spent some time messing around with that. If you use the other expressions that we have used for manometry, remember we've always had this positively upwards coordinate system, right-hand coordinate system, x, y, and z vertically upwards. Okay. So I think you guys know how to do that. Guys and gals know how to do that. Now, do we need? Is that just a replica of the other one? Actually, it's pretty close to being a replica of the other one. You probably get rid of that. If it's gases, again, the point is that this is absolutely true at a point, but not necessarily true as you go elsewhere. We know that, for instance, unit weight is equal to density times gravity. We know that pressure is equal to density, gas constant, and temperature. And so we can rewrite that, if you like, as density is equal to pressure over RT. And if you throw that in there, you end up with this other expression, which is, we've also played around with and integrated. We've done that. Been there, done that. So the other thing that's gone on, often when there's been questions, there's one about a balloon maybe 2 years ago. That was inspired by the fact that there's a balloon hovering above Life Sciences building when I came into class one morning. And so we talked about it, and we did some examples in class. And so you should also take that as a note of things that we've done in class might turn up. I know we did this in class. I'm not saying that in respect to this in terms of particularly. And if you do the derivations, you end up with a pressure as a function of a reference pressure and as a function of elevation and temperature and gas constant. And we've done that and we've played around with it. But as I said, there were no derivations needed, no integrations and derivatives needed. So the summary, I guess, in terms of fluid pressures at a point, the things we do know is that the pressures act uniformly in all directions at a point. We know that as you go horizontally, pressures don't change so long as you're in the same fluid. So long as you can get from A to B in the same fluid, however circuitous the path is, that you don't have to go into another fluid and come back out, then this is always true and means that you can kind of map pressures from one location to another. And this is always true at a point and in a liquid. This is always true everywhere at a point, and this is always true in a liquid. So I'm just repeating myself again. You know how to do things. And so I'm not sure this bottom picture is particularly relevant. Certainly pressures A and B have to be the same. Certainly pressures A and B here have to be the same as well. And you'll remember the example we did in class with the cylinder that was balancing at the edge of the swimming pool that had kind of a funky boundary condition attached to it. This was just relying on this fact that as you go from one location to another and you can get to it in the same fluid, then the pressures absolutely have to be the same. So, yeah, ciao. Yeah. Is that the question? So, yeah.
Are we supposed to assume that all gases on this exam are ideal or no?
No, you're supposed to bring the Peng-Robinson equation of state. No, I was just being facetious. Yes, you can assume that all gases are ideal. Mr. Smarty Pants. No, it's okay.
And my question is, with respect to the equation as P2P is equal to P1 exponent negative GC2 minus C1 RT0. Is that the equation I was supposed to use?
What was the middle part? No, I got it. Yeah, that's the equation you do. So that's isothermal if you go up in the atmosphere, right?
Okay. Awesome.
And we also did one in class for change in temperature, right? Yeah, fine. Yeah, no. I'm just giving you a hard time. All right, pressure at a point. What else do we need to know? We need to know, what about this? This is manometer. You know that pressures A and B prime are the same. We know as you go up in this column, the manometer equations, what are they? If you go upwards, you subtract pressures. If you go down, you add pressures. If you're in a vapor, you use the vapor pressure, or in a closed space. A test tube turned upside down, filled, and then turned upside down in liquid so it pulls away from the top. And what else do we know? And I guess in the gas, gamma gas is much, much less than unit weight of a liquid, not fluid. And so when you go up and down in the gas, you often don't have to care about pressure changes with elevation, right? So plate. You know that. So that was a barometer. You'll remember how to do these, of course. Start from a place where you know things. So if you want to calculate the behavior there, I think the easiest way to do this is just to write the pressure at a point you know minus 7 times unit weight red, and then thank you, minus 2 times, there you go, minus 2 times the unit weight of white equals PA. This point here is obviously simply connected, and so that's it. And so I think that's by far the easiest way to be able to write these expressions. And doing a bunch of different ways we've done it, but that's by far the easiest way. Of course, if gamma white is a gas, then you don't need this term, etc. Yeah, of course. Yeah. Gamma gas is a. I guess it's actually labeled here. I didn't really look very closely, but it's not in this particular case. I don't know that you need to know that hydrogen, mercury is 13 times the density of water, but that's just something that pops into mind. All right. So any questions on fluids at a point of manometry? So you go up, pressures go down. You go down, pressures go up. Gases, low unit weights, don't care about the pressure changes. Vapor pressure, if it's a closed space. And if you go horizontally in the same fluid, then the pressure doesn't change. Pressures on structures. What were the 3 important tenets we talked about? One was that we can calculate the magnitude of the resultant force by using some simple formula, which we'll go through. Depth of the centroid times the unit weight of fluid times the area of the plate. We can calculate the location where it acts by using the parallel axes theorem. It doesn't act at the centroid of the surface, but it acts at some other point, which is usually at least below the center of the centroid of the thing, or the centroid or below, I guess. The centroid of the plate or below. And if you want to look at failure mechanisms, you have to take the resultant forces and where they act, and then resolve around a relevant location as to where they might fail. And so, although you can calculate the forces and where they act by resolving around any point you want in the structure, to be able to look at some failure mechanism, you have to choose the right hinge or rotational point. And so those are the 3 tenets that we've worked through. And so we didn't really dwell on this, but you get the idea. So that makes the point that you have to be able to, if you're looking at this thing moving this dam, you have to say something about the failure mode of this. And so you've used that in some examples on gates in your assignments. And so I won't dwell on that to discuss that. Let's dwell more on the points of those three issues part by part. Where does the force, what's the magnitude of the force? The magnitude of the force is always given by this expression, which is magnitude of the force is equal to the depth of the centroid, unit weight, times the area of the plate. So in this particular case, this would be the area of the plate. If this is the centroid, and this is the surface of the water above here, I'm just going from this thing here, then this would be H sub C. H sub C is always the vertical depth, not the in-plane length. Always the vertical depth. And we've really talked about physically what it is. If this is the pressure distribution acting on this plate here, then physically what it is basically taking this location here, slicing off this triangle here, and adding it on here. And so that's why this length here is HC multiplied by unit weight, which is equal to the average pressure on this plate. this magnitude here. And so multiplying this average pressure by the total area of this plate, not surprisingly, gives you a force, the resultant force on the plate. So always vertical and always to the centroid of the plate, not the centroid of the pressure distribution, but the centroid of the plate. Doesn't matter if the plate is inclined or vertical, it's always the centroid of this thing, whatever it is, you know, the middle. The location where it acts is always at the center of pressure. We've not really used the term H sub r, we've preferred to use the term Y sub r. And we use the term Y sub r rather than H sub r because it's always measured in the plane of the surface. And so it's measured from the surface. My thumb is the Y coordinate. My first finger is the X coordinate. My first finger is on the surface of the water. And so the distance to the point of action, Y sub r, is the distance from my finger to wherever it acts on this point here. It's that way.
So it's within the same place.
Always in the same plane. Always in the plane of the plate that's being loaded. And that's important to remember. So if you think about the distinction between this, always a depth to the center of the plate, always an in-plane length from the surface to not the center of the plate, somewhere else. And we can calculate that pretty straightforwardly by the parallel axis theorem. Don't need to derive it, but you need to maybe be able to use it. And it really says that if the water surface is here, on this line here, the x-axis, you can calculate exactly what this is, which you'd like to know, because you need to know where it acts. If you know the in-plane length to the centroid, so the in-plane length to the centroid is the middle of this, you know, it's its balance point, the center of this plate. And so it would be this length here, this length here. But the point of action of the force is always somewhere either at that point or below it, always. And you can see that from this expression, right? Because it has at that point, which is the location of the centroid, or some distance below it, always positive. And you can get this if we know this, you certainly know this. If you know your area from this calculation here, you certainly know the same area here. And so the only tough part is to get this second moment of area about the centroid. Yeah.
Like for like an irregular cross section or something like that, should we have them all on an equation sheet, or like would we want to be provided?
I bet you'd be given it. Wouldn't hurt to have it on an equation sheet, but I think you'd be given. I think in the past we've given you.
Yeah, those more on past exams.
Yeah. So b cubed over b cubed a over 12, right? So these things just roll off your tongue. You know what they are. But yeah, you'd be given it, I think. So you need to be able to calculate this, and so we have some expressions for those, and so you know that. So these. We can calculate it around the x-axis as well. Not so important because often these things are symmetric and they all balance, and so that's a bit of a stretch, I think, for a midterm exam. But certainly know this. Clear. So y is in the inclined plane, and so that's the important thing to know, right? So everything we've talked about now has been forces on plane structures, like this. And so if we want to look at things which are different from that, then we can do that. Did a couple of examples in class. We can resolve things. As we said in class, it's an artificial example, pardon me. And we certainly wouldn't want to do an artificial example. Because it's artificial because why would we care about half of it? We care about the whole thing, in which case the reaction for this thing is just the same reaction up here. But I guess it served a purpose. What were the lessons from this, I guess, for this curved surface? I guess the lessons were that because all the pressures act normal to this surface, they all act through this point, and so the resultant has to act through this point. When we resolve the horizontal force that's acting on here, these two have to be equal to each other. We can certainly calculate this, and so therefore we can get this. We can certainly calculate this from a volume times a density times gravity, and so we can certainly get this. And so there's no doubt that we can get both of these two components from things that we already know. And if we know that, we can use Pythagoras to be able to figure out what the resultant is, if we so wished. And we could also figure out where it acts, because it has to act through this point here. And so we went through that. We know the behaviors for simple shapes is that for triangular pressure distributions, the point of action of this is 2/3 of the way down here and 1/3 up. You'll remember that from your other physics classes, for instance. And we will not have anything in English units, imperial units. And so you'd calculate from Pythagoras the location of action. Okay, yeah, ciao. Go ahead.
Like in a dam where it's triangle shaped, does weight act?
A concrete gravity, a dam like this, you mean?
Yeah.
The centroid of that would be the same as the centroid of any plate. It would be 1/3 away. It would act 1/3 of the way in and 1/3 of the way out. Yeah. So if you wanted to balance that triangular sheet, that's where you'd balance it. And the reason that we kind of know that slightly is that if this, for instance, instead of being a dam, was actually a pressure distribution, then the actual we know that the resultant of this acts at this point, right, due to that pressure. But also the weight of that would do as well. What else? Another more complicated one we went through. I'll go through it if you want, but me not going through it might be a good thing for you. Other examples, we went through this in class, I won't go through it. The only interesting point was this, I think, is that typically you'd think at this point that the pressure would be equal to atmospheric, but it's not, right? And you know it's not atmospheric because this is simply connected to this point here, and of course this point here has to have the pressure is equal to H unit weight. And so if you looked, for instance, at the pressure distribution on this point here, it wouldn't start at 0 here and go down like this. It would start at whatever this magnitude is here, P, this length here, which would be this. And so, again, just a curiosity, maybe more than anything else, and something we went through in class. I think that was the only trick in that particular one, apart from the fact that it was also in English units. So this I did last year after this review session. So it's exactly a year old tonight. Not yet born yet, I guess. And it's to show the commonality between all the methods that we've talked about. You should get the same results regardless of how you go through these. And so really it is an example that basically talks about a structure, and that structure, I suppose, is some plate that looks like this, that happens to be 1 meter thick, and I guess 1 meter deep, 1 meter in, and so this obviously, not obviously, but this is square root 2. So this is a plate that has some area, and which is holding water back behind it to a depth of 1 meter. And so it's a simple geometry that just proves to illustrate the point that by doing this all manner of different ways, you should end up with the same resultant for whatever the force is that acts on this, and also the location where it acts. So you can use the magnitude of the force, which is equal to, right? These two are the average pressure, we just said, acting at the centroid of the plate, multiplied by the area, and the magnitude of the force, resultant force acting on this, Fr, has to be given by this. So the depth of the centroid is 0.5 meter, presumably. The area is square root 2 times 1, and the unit weight of water is water. And so you end up with some number as a function of that. If you want to calculate where it acts, you can use parallel axes theorem. The y-coordinate of the centroid would be square root 2 over 2. It would be half this distance down here. This is square root 2 over 2. This is y sub c. This is the 1 over 12 times b times a cubed. 2 square root is just the length of this, right? So 2 square root cubed is the length cubed, and divided through by the depth of the centroid, which is the same as this. This is also this. And multiplied by the area, square root 2 over 1. And so if you work these out, you end up with a force that's applied in kilonewtons, actually acting upwards on this if you think about it, and also the location where it acts, which should be 1/3 of the length along the dam. The other way to do it, entirely consistent with that, is this pressure prism approach. So you take the dam on its own. You take the average pressure. This is what we've called P prime. Actually, this is the same expression as this one, just written a bit differently, times the area. And you get the same force that's acting on this. And we know that for this triangular pressure distribution, not dissimilar for the question it was asked about where does the weight of a dam act. It's 1/3 of the way along it because this is the pressure distribution, and so the force has to act 2/3 of the way down from here, and the total length of this is square root 2. This is this length here, and so 2/3 of square root 2 is the location where it acts in the plane of the dam, and this is exactly the same as the one up. So that's two ways to do it. So parallel axis theorem, just based on pressure prisms. This happens to be 0 because it intersects the surface here. And the final way to do it, if you really want to torment yourself, or have to do it this way, is to go through this and isolate. So this is the gate, side on, that has some unknown horizontal force acting on it and some unknown vertical force on it, or some resultant. We don't know any of these. But what we can do is we can isolate the water in here and look at what forces we have to apply to keep this free body intact. And if we do that, we have to accommodate this weight of the water. We have to have a resultant that's due to this pressure distribution, and we have an upwards resultant due to the fluid pressure that's acting on this underside of the component. And so we can certainly calculate this from the volume of this wedge of water. We can certainly calculate the magnitude of FH from knowing what the area of this side is and multiplying that area by the average pressure. And we can certainly get the average pressure at this depth of 1 meter. Obviously, not obviously, the pressure here has to be equal to the depth of the centroid of this plate, which is sitting here, times the unit weight, times the area of that plate. This is average pressure. And so if we know all of these, we know enough to be able to solve this. So a little bit more involved, of course. I don't know if you want me to go through it. I don't want to bore you if you don't want me to, but certainly you should think about seeing what the individual components of this are. I think you do not have to use something quite as involved as that. If that's what might make you happy, then that might be a useful statement. Okay. So it's important to realize maybe that the methods we talked about to get forces acting on structures and where they act are really they should all give the same result. So they're not. It's not a choice of one or the other. It's just which works best in a particular situation. Buoyancy, flotation, and stability. You know that the buoyant force is equal to the unit weight times the volume of water displaced. So this is the volume of water displaced, and this is the unit weight of the fluid, whatever that is. I guess it could have been, maybe I should write it not as water, but the unit weight of the fluid and the volume of the fluid. And so we know that. We can resolve behaviors in terms of looking at resolving forces. If you have a buoyant force that's acting up here, if you have a weight of this buoy, and you also have a tension in a cable, then that's basically the system that you have here. Then you can write a free body, and if you know what the volume that's displaced is, and you know what the weight of the body is, you could calculate, for instance, the tension. I suppose if the sum of these two is greater than the buoyant force and the weight is greater than the volume of water displaced, then it would sink, and you'd have to apply a positive force. And so we've done that. And so that's what we've done to apply to buoyant forces. Buoyancy force acts at the center of buoyancy, which is the center of the displaced water mass, center of gravity of the displaced water mass, the center of pressure, which is equivalent to center of pressure. The center of gravity acts at the center of the balance point, if you like, of that solid structure. And so we talked a little bit about how you could look at stability based on that to be able to define that. Okay, and so finally, the last thing is part 4.1, which we talked about accelerations. We talked about linear accelerations and rotational accelerations. We did two things. We looked at these expressions that define rates of changes of pressure in space, and we wrote them so that we could define a surface that had a zero pressure change as you went along it, and so it was atmospheric pressure. And we could define the inclination of that surface, dp, I guess d z dy, as we called it. And the other thing we talked about was what happens to pressures, for instance, as you go down in the fluid, if it's accelerating horizontally. If it's horizontally, it's just the same as if it's static. If it's accelerating vertically, then the pressure change either increases as you go with depth or decreases as you go with depth, depending on which direction it's accelerating in. And so we'll just quote the results, not the derivation, and that was that we could calculate the slope of the surface in a system. So this here is a slope. If I do this, this is change in elevation with location as you accelerate something horizontally in the positive y direction and vertically in the positive z direction. So in other words, in this case, it's doing this, right? So not just constant velocity, but accelerating. Otherwise, it wouldn't take up this form. And so from that, what do we know? We know that if it's not accelerating horizontally, then it's just equal to, it's constant. It's actually, well, 0, right? If AY is 0, then the slope is 0. It's just flat. If it's accelerating horizontally, it goes with some inclination. And I guess the only other thing that came out of that was that if you look at the fluid pressure changes with depth, then if it's accelerating, if the fluid is accelerating upwards in the z direction, so this would be AZ, positive Z, then the pressure distribution with depth would be greater than if it was just a static fluid. And we know that because this is our new expression. And so if you want to write that out differently, it would be dp dz is equal to minus unit weight minus density times the acceleration in z. If the acceleration in z is 0, then it's just our old friend. If the acceleration is finite, then if you're going up in the elevator, then it gets higher pressure at any given depth as you're accelerating upwards. If you're accelerating downwards, then it's the opposite. And of course, you can use this to be able to calculate what the fluid pressures might be on the side of a container if you wanted to. So if you're going down, accelerating downwards, then the pressure distribution was the one that I've kind of colored in here. So if the acceleration is negative, meaning going down. So linear accelerations is one of them. Rotational accelerations is the other. Seems that we're going around in a circle, and therefore it's going at a constant rotation rate. But the idea is that instead of being able to go at a tangent to the string that you're throwing it at, it gets pulled back in, and so it's changing velocity all the time, angular velocity, and so it accelerates in an angular mode. And again, we can just quote the results. One is that the pressure change with radius changes as a function of how far out you are. The further, longer your string is, the larger this, the steeper this curve becomes. This is kind of dPdr, right? Not quite, but if the fluid's more dense, it changes as you go out. And if you're swinging it around faster, then you double the speed at which you swing it around, then you quadruple the slope of this. So what else should you remember? You should know that the rotational velocity is equal to the radius multiplied by the angular rotation. We've seen that before. So this is v theta, this is r, and if this is the fulcrum, this is the angular velocity. What else you should know? You should know that omega is in radians per second. And you should know that 1 revolution per second is equal to 2 pi radians per second. And so if you have that, you can use that to be able to say something about, again, two things that we did. I guess we said something about how the slope changes as you go out through this. That the elevation is equal to this rotational velocity, the location where you are. So this just is radius here. And if you use this equation, you have to zero it first by figuring out exactly what the constant is, if you're trying to figure out this surface. So again, as in the case for laterally accelerating fluids, we did two things. We said, one, we can figure out exactly what the slope of this fluid is as we go across it, dz, dx, dy rather. And we can also figure out exactly how the pressure changes as we go down through it. When we dealt with fluid pressures due to rotating fluids, we did exactly the same thing. We figured out what the surface would look like. This case is not dz, dr. It comes from this, but actually we have to integrate it and then use this expression. And so if we want to be able to use it, typically we have to figure out exactly what the constant is by knowing what this behavior is at some particular point. And we talked about an example where we didn't do the example, we talked about an example where we zeroed the expression here. And the other thing is we could use it to calculate how the pressures change with radius as you go on a horizontal through a fluid. Again, you have to figure out exactly what this constant is by doing it against some geometry that you know, where you know the elevation or the pressure at a point, and then you can extend it by figuring out what this constant is to figure out what the pressure would be at any other location you might want to choose in terms of elevation and radius within the fluid. And I think that's it. So very, very similar behaviors. So that's kind of it. I'm happy to stay and talk about things that you want to go through. So it is everything that you need for this test should be in those 20 odd pages or so. Think about how you've done examples in class and done them as assignments, and I guess we're done.